we're going to find the area of a region. We're going to start out with an example that is familiar to us, the one that we've done before. We are going to do it in a little bit different manner, and that's just to help us with the problems, the more difficult problems that we are going to work with today. So we have the information, we have the area is in the first quadrant bounded by x is 0, y is 0, and y equals 16 minus x squared. Now you do need to know how to graph these and what area that it's representing. So I've done that for us. So what I'm going to do, if you remember when we were first finding area underneath a curve, we did a lot of estimating. So we started out, we did counting squares, we did Riemann sum, we did trapezoidal rule, Simpson's rule, and all of those. So with this one, we're going to kind of approach it how we did Riemann sum. So we had rectangle. So I'm going to draw one representative rectangle. And this is the point x, y on our rectangle. So if we were looking for just the area of this rectangle, we're going to make the width dx. It's some change in x. We're not sure how wide it is, so we have a change in x. And then the height would be y. So just this area, so our one representative area, is found by taking y times dx. Now having more than one variable for our area with y and x isn't going to work for us. So we're going to say, well, what is y? Y is 16 minus x squared. So then that's just for one of our rectangles. So imagine we took and added a bunch of the rectangles, and we did these infinitely small. Really what we would be doing is finding the integral of all of these rectangles, or adding all of those areas together. Now we do need our limits of integration, so we need to know where it is intersecting. So we have this point here, which would be 4, 0, and this one, which is 0, 16. Now we have 4 numbers here, but we really only need 2 of them for our limits of integration. And we're going to talk about, well, all of our variables given are x's. So we should be using the x numbers, which are 0 to 4. Now you do know how to calculate these without our calculators, but for our time purposes, we're going to grab our calculator and work that out. So we'd get 128 thirds, which is also 42 and 2/3, which also can be estimated to be 42,667. Remember, area is measured in square inches or square meters or square units. Let's go to our next example. Let's do a little bit more difficult one. So our next one is we have the area between 2 lines. Again, you do need to remember how to graph these by hand and also on your calculator. So do know how to do both of those. So I've graphed it again for us. We're going to do the same idea with this one. So I'm going to drive one representative rectangle. I know the width is dx. And so I'm like, well, what is my height? So imagine if there was a point on each line. So we'll say this is x1, y1, and this point is x2, y2. And I'm going to go back up to here to our functions because we know that our parabola would then be y2, and our linear equation is y1. It's helpful to know later. So if I was looking for the height of this, I would take the larger number, which is the y value above or on top, minus the y value on the bottom. So the overall area of that rectangle would be y1 minus y2 times the change in x. And again, we don't want to have two different variables. So we have a change in x, so we want to get our y's in terms of x. So our y1 is the line, negative 3x plus 5. And the second equation is our parabola. Times dx. Now you might want to simplify this. So I am subtracting them. So I'd have a negative x squared and then a negative 3 plus, I'm sorry, negative 3x plus a 6x would be a 3x, and 5 minus 3 is 2. So that's one of our rectangles. So if I imagine I drew a whole bunch of rectangles here, I can do all of them and add them together. I'd be really doing the integral or the sum of all of those rectangles. So now with this one, I do need, again, my limits of integration. So I need to know the ordered pairs in which our two graphs are intersecting. So to me, it looks like around negative a half and 3.5 approximately, but we can't work with approximates. We do need to know the exact values. So we're really looking for, well, when are the two lines intersecting? So then I'd have x squared, add the 3x, and subtract the 5. Now this should look familiar to you because really we're just finding where are they the same. It is the same as this, except if you moved everything to the other side. So if you recognize that, you are correct. That is true. And so now I'm going to solve this. And you can solve these with your quadratic formula. So negative b plus or minus b squared minus 4 times a times c all over 2 times a. We want to work with exact answers. We don't round until our very final answer. So when we go up to here, it'd be 3 minus square root of 17 over 2 and 3 plus square root of 17 over 2. And again, we can work this out. You could do it by hand because it is just a polynomial, so it's not very challenging. But we're going to save time, do this on our calculator, so take a minute. So if we do math 9, which is function integrate, negative x squared plus 3x plus 2 on x from 3 parentheses 3 minus square root of 17 divided by 2 to 3 plus square root of 17 divided by 2. You could also, on your calculator, graph the 3x or negative x squared plus 3x plus 2, graph that and calculate the area underneath the curve as well. It's up to you how you do it. Just again, make sure that you're using the exact values and not the estimates. So this gets me 11.682. So both of these were with respect to x, but what if we had to do a problem with respect to y? So we're using our y is our variable. And so this one, we're back to the same example we did before. Tried to keep with a simple example to start with, and then we'll do a more complicated one. So if we go back to this one, The process is going to be the same. So we draw a representative rectangle. Then we're going to list what our dimensions are. So on this one, our height is the change in y. We don't know what the change in y is, but that's what it that side would be. And then this side would actually be the length of whatever x is. So if I were to write my area, I have base times height. And again, can't have our two different variables, but since we have change in y, we want to take this original equation and solve it for x. So I would have x would equal the square root of 16 minus y would be its equivalent. So we have that each area would be the square root of 16 minus y times the change in y. And so if we're looking for all of our area, we have the sum of a number of rectangles. And again, we need our intersections here. So we know this is 4, 0. This one is 0, 16. And this one, we have a y and a y, a dy, everything's in terms of y, so our limits of integration should also be in terms of y. Now we've already solved this area, but we should check it on our calculator. When you do it by hand or on your calculator, it's up to you. You should know how to do both ways. When you do the function integration on your calculator, you can use x's instead of the y's, or you can change it to the y. Just make sure when you say in terms of, so that the function in comma, you're using a y instead. And we already found this before, and we said, well, it's 42 and 2/3 or 42.667 if we round it. So that's how we're going to do it in terms of y. So let's approach one of those problems. So we have the area bounded by x equals 4 minus y squared and the line y equals x. Now graphing the line y equals x is not very challenging. However, x equals 4 minus y squared might be challenging. So let's just go back to when you first learned how to graph. And you know that this would be, if it were x's and y's were switched, it would be an upside down parabola with intersection at 4. So our graph is still going to have an intersection at 4, but instead of being 0, 4, it's 4, 0. It's switching the x and the y coordinates. So that's where that point is coming from. And since it's negative, instead of opening down, it will open towards the negative values, which will be to the left. If you need a few more values, this time plug in for y to find x. So if I plug in 2, I'll have 4 minus 4, which is 0. Same will be true with negative 2. I can do the same for other values if I wanted to. I'm not going to take the time to do that, but that is how you can develop that graph of variables or equations given in terms of y. So this is our resulting function. Now I want to talk to you a little bit why we would choose to do it with respect to y. So if I do a representative rectangle here, it's fine. I'm going between one line and the second line. But however, if I do one over here, I'm going in between that parabola. So if I take parabola minus the parabola, I end up with 0. So that's not going to make sense to do. So that is why, or this would be in a case that we would do a horizontal rectangle or with respect to y. So again, we have our dy as our height. We do have two coordinates here. We have one x1, y1, and then this one x2, y2. And I'm going to go back to, so the line was our y2, x2, and our parabola is 1. So just line 1 and line 2. That's helpful to know. My width would be the change from x to x. So, or x2 is smaller than x1. So I always do larger minus the smaller. If you know what the coordinates were, you would take the larger minus the smaller. You're going to do with the x variables as well. So now I'm ready to write the equation for just that representative rectangle. I have my base times my height. And again, I don't want things in terms of x's. So my x1 is on my sideways or horizontal parabola. And our x2 is on that line, y equals x. So my area would be sum of all of these. And if you want, you can rewrite it. I'm going to do that just because it makes more sense to me to rewrite it. So now the only thing missing are the points of intersection once again. The points of intersection are not necessarily challenging to figure out because it is just where the two lines are crossing. And you'll notice when I'm solving this, I'm going to end up with the same equation as I did as part of my integral. So again, if I do quadratic formula, I would have 1 plus or minus the square root of 1 squared minus 4 times a times c will be 17. It's just a coincidence that those happen to be the same over negative 2. And then those look like it's around like 1.5 and negative 2.5. You can check those. Now this one, it's important that you get which one would actually be the bottom one. Since you're dividing by the negative 2, the 1 minus square root of 17 would actually become the upper one because you're dividing by the negative. If you wanted to, you could, quickly figure out, well, what would those decimal equivalents be? What I'm going to do is I'm going to get those and now plug it into your calculator or work it out by hand. So math, function integrates. You could also, again, remember, graph the resulting and use that function or calculate the integral as well. Just give me a minute to do this. And I get 11.682. So remember, draw your representative rectangle. Make sure that you're using with respect to x and with respect to y appropriately. And then find the points of intersection. Make sure that if it's in terms of x, you're using x values, and with y's the same. And then calculate. Do make sure that you do know how to find these areas with and without a calculator. I did show only the answers, and I did it all on the calculator, assuming that you do know how to find